So what is the greenhouse effect? Well, the greenhouse effect is just a name for talking about how a planet's atmosphere affects its temperature. So let's start out by talking about a planet without an atmosphere. So here's a planet right here. Color it in. There's my planet, and it has no atmosphere. So what's happening to this planet when we plop it in front of the sun here? So light comes in from the sun, or whatever star this is, comes in, and the light from the sun is mostly visible light. But some of it is also infrared. And infrared, I'll just write IR for infrared. IR. And really, there's more than just visible and IR light. There's also some ultraviolet light, which is just a little bit higher frequency, and some other light, but most of it is visible light, and there's a good chunk of infrared light as well. So anyway, this light comes in from the sun, it hits the planet, some of it bounces off, so bounces off maybe over in this direction, bounces in many directions, and this light bouncing off is actually how you see the planet in the first place. So maybe you're in a spaceship over here. If you're in this spaceship, this light bouncing off the planet at your spaceship, at your eyes, is actually how you see the space or see the planet in the first place. But that only happens to some of the light, and the rest of the light is absorbed by the planet. The planet absorbs the energy in the light and then heats up. So now you can ask the question, does this happen forever? Does the planet keep getting warmer and warmer and warmer until it eventually becomes its own little mini star? So you might intuitively guess that that's not the case. Planets do actually reach a stable temperature. And they do that by radiating energy away from themselves into space in the form of infrared light. So I'm drawing these sort of pink arrows in all directions to try to show that. And this phenomenon where an object shoots infrared light away from it, it's called blackbody radiation. I'll write that down. So blackbody radiation happens to everything. It happens to anything that has a temperature above absolute zero or 0 Kelvin. If you've ever seen a hot piece of metal, say at a blacksmith shop or a picture of a blacksmith shop glowing red, that's because of blackbody radiation. If you've ever seen a thermal image where maybe you take a picture of something in the woods and you can see an animal sort of glowing, that's also because of blackbody radiation. The animal that's warmer than its surroundings is shooting out more light than the rest of its surroundings. And then you can actually, using a camera that's sensitive to infrared light, you can make an image of that. And even the sun is a black body, or radiating like a black body. Finish writing this word here. Blackbody radiation. And the term black body is a little bit confusing. The sun, for example, is emitting light largely because of blackbody radiation, but the light that is being emitted is not black. So it's a little bit confusing, but for some historical reason we call it blackbody radiation. But coming back to this planet, we know that the planet, if it's going to reach a stable temperature and be there constantly for a long time, the energy coming into the planet has to be equal to the energy coming out of the planet. And we can write an equation to express this idea. So I'll write P out. So P stands for power, which is just the rate of energy transfer. So P out is equal to P in, which is the rate of energy transfer into the planet from this light. So is it possible to figure out what the temperature of this planet will be just from knowing about the energy that's hitting it and the energy that's flying away? Well, it turns out that is possible. And that's because blackbody radiation has been studied in some detail, and we can actually write an equation that tells us how much energy or how quickly energy is radiating from an object based on its temperature. So that equation is the P out, so the rate of energy radiating away, is equal to, change colors here, the surface area of that object. The more surface there is, the more opportunity to radiate away there is. Then there's a constant called the Stefan-Boltzmann Constant, multiplied by the temperature of the object to the 4th power. And this is the temperature in Kelvin. Now if we solve this for T, we get T equals, so we can divide both sides by the area and the Stefan-Boltzmann constant, and then take the 4th root of both sides to get T alone. So we'll end up with this P out, divided by A and sigma, which is the symbol for the Stefan-Boltzmann constant. Then we'll take this, not the square root, but the fourth root. So if we can figure out what P out is and what the area is and what the Stefan-Boltzmann constant is, we could actually just calculate the temperature of this planet. In this video, we're not actually going to carry out a calculation of this, but let's just look at the pieces to convince ourselves that we could calculate it. So the P out, we said, is the same as the P in, the rate of energy entering the planet. And we could find that by looking at the intensity of the light coming in and then also looking at the cross-sectional area of the planet here. So we could picture this light hitting some disk here. So say this is a disk facing the sun there, and we could think of all of the light landing on that disk, and that makes it a little bit easier to figure out how much energy is actually hitting the planet and being absorbed by the planet. So in that way, we could find P in, which would give us P out, and we could plug that into our equation. The Stefan-Boltzmann constant is a known constant, so we don't really have to worry about that. We would just have to look it up. So the area, this A here, is actually the surface area of this entire sphere, so we could just use the formula for the surface area of a sphere, plug it in here, and then we would have an expression that we could evaluate. We could multiply and divide, take the fourth root, and end up with a temperature. And we'll actually carry that out in the next video. Now let's look at another planet. Here's another planet, slightly more oblong than the other planet, but it'll do. Color it in. All right, and this planet actually has an atmosphere. So I'll draw an atmosphere around it, kind of exaggerate the height of the atmosphere. It almost looks like a fried egg. And it's the morning, getting hungry. But anyway, here's a planet with an atmosphere. Now let's look at what happens as sunlight comes and hits this planet with an atmosphere. So it starts out the same way. Light comes in, it hits the atmosphere. And now we run into the interesting fact that many gases are transparent to visible light, but opaque to infrared light. So as this light comes in here, some of it bounces off just like before. Some of it bounces off. Some of the infrared radiation is actually absorbed by the atmosphere. And then the visible light just travels on through and hits the surface of the planet. Now again, as this planet heats up, it starts to emit infrared light. Infrared light comes out all directions. All right, so there's my infrared light coming out. But like we said before, many gases that make up the atmospheres of planets are transparent to visible light, but are opaque to infrared light. So this light gets absorbed into the atmosphere. So instead of flying off into space, off far away from the planet, the energy gets absorbed nearby the planet in the atmosphere. And the atmosphere heats up. And when the atmosphere heats up, it also emits light. It's not exempt from the blackbody radiation behavior that all matter exhibits. So it too radiates infrared light away from itself. So it radiates it out, but it also radiates back in toward the planet. So I'll draw a few more arrows here. Arrows in. The squiggly arrows are too much for my lackluster artistic skills. But anyway, we can see that it is radiating some heat out, some light, some energy outward. So this whole planet atmosphere system is still able to shoot light away from itself and at some point come to a stable temperature. But this time there's an extra step in between. And now instead of just one source of light, one source of radiation, or one source of energy hitting the planet, we actually have an extra source, which is this warm atmosphere radiating this heat back at the planet.